Sampling distributions. What is a sampling distribution of a statistic? Think of it as a collection of all values of a statistic when made into a histogram. What patterns emerge? For example, let's create a simulated example. I'm using a package called Minitab because of how easy it can be to make samples and calculate the needed values. You will not need to know these details. I'm going to start by creating observations of categorical data. Suppose that 20% of all vehicles are made by Toyota in this area. So the chance of observing a random vehicle and it being a Toyota is 0.20. I'm going to ask the computer to act as if it's taking samples of 100 vehicles at a time, which will be each row, and then do this for 100,000 different samples. The values are all zeros and ones. In the computer, a 1 is a success, or it would be like observing a Toyota. A 0 is a failure or a non-success. So if I simply add the zeros and ones together, it will be like counting the number of Toyotas in each sample of 100. I do this in Minitab using the Calc menu and then selecting Row Statistics and Sum. Then I enter columns C1 through C100 and store the result to get the sum for each row. Notice the last column, 101, now is the number of Toyotas, or the sum in each sample of 100. To get the statistic, the sample proportion, p hat, I use the calculator and simply find the number of successes in the sum column divided by 100. Now the p hat column has 100,000 values of the sample proportion. This is an approximation of the true mathematical outcome, but let's create a histogram. From this graph, notice that the mean of the sample proportions is near 0.20. The descriptive statistics will help approximate the standard error of the proportion, or the standard deviation of all possible p hat values. Now Minitab can calculate those for us. So the mean and standard deviation for these 100,000 values are estimates like the values we expect for mu sub p hat and sigma sub p hat. Now in the mathematical theory, the math says that mu sub p hat should equal p, which was 0.20. Sigma sub p hat should equal the square root of p times 1 minus p over n, which equals the square root of 0.20 times 1 minus 0.20 divided by 100. That equals the square root of 0.16 over 100, or the square root of 0.0016, which is 0.040000, or just 0.04. Notice here the standard deviation is very close to the 0.04 and the mean is very close to the 0.20. Also notice that n times p would be 100 times 0.20, which is 20, and that is at least 10, and n times q is 100 times 0.80, which equals 80, and that is also at least 10. So the shape of the histogram should be like that of a normal curve. So the simulation should show a histogram that is approximately symmetric and mound-shaped like a normal curve, with a mean of 0.20 and a standard deviation of about 0.04. So the edges should be about 3 times 0.04 on either side of 0.20, or from about 0.12 or 0.08, I should say, up to about 0.32. Hopefully this helps to understand the values of the sample proportion can be different for different samples, but yet still produces a normal looking curve from which we can create z-scores and find probabilities.